Okay. Thanks. To begin, I'd like to ask that we take a very brief moment. Since I come from the world of human rights, I'd like to read to you Article 27 of the Universal Declaration of Human Rights, which reads that everyone has the right freely to participate in the cultural life of the community, to enjoy the arts, and this is my favorite part, to share in scientific advancement and its benefits. So, speaking to you from the human rights world, I ask you to celebrate this particular human right, and I have a sticker, which you can have if you come and ask me for one, that you can put on your electronics, inviting other people also to share with us all in this right. I'll talk to you today about our work with my colleagues at the Human Rights Data Analysis Group, working with lists of deaths in conflict. I'll refer to several different conflicts, but the one that I'll be using as the example are deaths recorded in Syria since 2011. The problem with deaths in conflict is that people are recording these deaths often in near real time, and the people recording the deaths may not know the person as intimately as we'd hope. There may be no official records that they can use to make connections. These are deaths recorded in Kosovo between March and June of 1999. People may record components of the person's identity with errors, particularly the location or date of death may be an error, and other data that is less accessible to the person doing the documentation, such as the location of birth, the parents' names, or the date of birth, are very likely to be full of errors. So we've been at this since 1999. We've done it in Guatemala, Kosovo, Peru, Colombia, Timor-Leste, El Salvador, Liberia, and Syria most recently. And of course, each of those countries poses different kinds of challenges because of people's relationship to literacy. Different levels of literacy lead to people's differing levels of precision in the details they recall about people's identity. Name spelling is only the most obvious of those, as well as different structures of names. People in different cultures record names in different ways, and consequently we get different levels of detail about that person's identity. Our technology has also evolved. We had a unitary software tool which was written primarily in Java, which we used for the first number of years, but since in the last 4 or 5 years we've evolved into a series of small tools joined loosely together, which we take from the overarching Unix philosophy of tool building. And then we found this a lot easier. The toolkits we use now are primarily written in Python. We use pandas, SciPy, NumPy, scikit-learn, and FastCluster. We use R for descriptive statistics and exploratory graphs, and to do the estimation that I'll link to at the very end of this talk. The point of all this work is to figure out how many people are not in our lists. So we use a variant of capture-recapture. I'm not going to talk about that today, but that is the goal. The data that I'll talk about today comes from fieldwork conducted by the Violations Documentation Center, the Damascus Center for Human Rights, the Syrian Network for Human Rights, and the Syrian Center for Statistics and Research. These are people who have teams on the ground in Syria. They are Syrian, and document deaths as they occur in near real time, and then send that information to teams in other parts of the world who aggregate them and then share them with us. There are a lot of data that get written down, and very often when victims are reporting the observation of deaths, they'll say something like, "I saw 4 bodies, but of course I was fleeing. I was running away because the bombs were falling or people were shooting at us." So what do we do with information about 4 bodies without identification? And our rule has been that we exclude that. We do not include information unless we have a record that includes at least 2 name tokens, a date of death, and a location of death. Otherwise, we can treat it as interesting information but not usable for database deduplication or for estimation. I won't review all of these since many of these people are in the room, and I'll try not to embarrass them beyond the necessary, but I deeply appreciate the enormously important work that's been done by the people listed on this slide. We did not make up this stuff. We're just bolting it together and writing occasional bits of code to pull the pieces together. And our framework looks, perhaps unsurprisingly, very much like a table of contents from one of Peter's books. We import the data, we generate pairs using blocking or indexing. We call that step pair gen. We compare the data sets, by which we mean we generate features for each record. We classify by training some sort of classifier. We cluster the data, and then we export it. We run a parallel, we maintain a parallel stream for the training sets. So we import training data, we integrate the data, removing duplicate pairs and assessing inter-rater reliability, which I'm going to spend some time talking about. We generate features for that data, and we also model that, and we use that model to do the classification for the other pieces. So I'm going to boil down the steps and only go into detail in a couple of the steps, in particular pairgen. We found a couple of different really great papers that I cited earlier that talk about ways to optimize the blocking process. Now, relative to many of the projects that are being presented at this conference, we have not that many records. We have about 420,000 records that we're working with right now. But that's still computationally intractable to manage all of them. You get something like 85 billion. That's just not, that's too many pairs to consider. So the process that we use to do this reduction to a smaller, more tractable set is to reduce, the notion is to reduce the number of pairs to the minimum necessary, and we call this the reduction ratio. So one of our two metrics that we're going to be working on in any kind of pair generation rule scheme is what is the reduction ratio that we're achieving with that scheme. But we can't just reduce it all. I mean, we could treat no pairs and have a perfect reduction ratio, and that would be useless because then we wouldn't be doing any work. So balancing the reduction ratio is pairs completeness. So given a set of training pairs that have been human labeled as a pair that is actually referring to the same person, a coreferent pair, given that set and given a set of rules, what fraction of all of the positively labeled pairs are covered by the rules? And this is called pairs completeness. And our goal is to balance these two. So what we've decided is we're going to take the simple mean of the pairs completeness and the reduction ratio at each step in an iterative process of adding rules. So what we do is we take all the possible, we generate a rule for each column that we can use for blocking, and common values in a column define a block. We then create conjunctions of columns. So another set of blocks is blocks that share a value on one column and values in a second column. And then we can create conjunctions of arbitrary length. We go to 3. So we'll say a block is defined by all the records that share values on this column, and a third column. And we compose those triples for all the possible columns. That constitutes our set of possible rules. And then we, at each step, choose the rule which maximizes the mean of pairs completeness and the reduction ratio. We discard all the pairs that are covered by that rule and pass to the next iteration of the loop and repeat this process. And what we end up with for Syria are these rules. So in each set of parentheses are the conjunctions, and then they are ORed together. And this is not something we would have ever arrived at by hand. This is a very, very complicated set of rules. But it turns out to have terrific coverage and a really good reduction ratio. So just to read the first one, this is a rule that says all of the records that share the first metaphone in English, in a translated version of the person's name, we took the first metaphone in their name, and shares the last metaphone in their name, and shares the year of death. So that's one block. That's one blocking rule that defines a set of blocks. So we'll take all those pairs and we'll consider them. Or, which is to say, we'll also take all the pairs in the second rule, which share a date of death, a governor of death, and a locality-sensitive hashing block defined by the sorted name also in English. So that's another kind of block. So each of the ORs add additional pairs that we will consider. And the outcome of this looks like this. So in blue, well, it turns out to be purple on this projector, you can see the increasing number of pairs that we have to consider, and in green, the decreasing number of examples that we have failed to cover from our positive pairs. So after about 6 or 7 of the rules, we pretty much are at the optimum point. And the outcome was that we reduced the total number of possible pairs to consider in blocking from the 86 billion sort of naive case, and using about 134,000 positive match pairs that the oracle has considered. And by the way, our oracles, thank you for that term, Peter, because they love being called oracles. Being called matchers didn't seem nearly as exciting to them, but now that they're oracles, wow, I think we have to pay them a little more. The oracles have considered about 134,000 positive pairs among the about 600,000 pairs that they've considered over the course of this project, and we are able to cover all but 481 of those with 44 million candidate pairs. So that's a 1,000-fold reduction in the possible pairs to consider, and perhaps more importantly, a 10-fold reduction relative to the handcrafted blocking rules that we've been working with for several years, where we tried to figure out what the best mix of blocking rules would be. Well, we can do 10 times better taking this approach. So that's one of the sort of pieces that comes out in practice, I think, from this stuff. So I'm going to turn now briefly to feature generation, or the compare step, and say that we find the kitchen sink approach really works for us. We throw every possible way to generate features at this problem. And as some examples, we look at name subcomponents, prefixes and suffixes. We sort the name tokens and take prefixes and suffixes. We'll take simple equality of those pieces. We'll also do locality-sensitive hashing to identify blocks and use the block identifiers, not only in the blocking step, also in the classification step. We'll use Jarrow-Winkler scores to compare edit distance. We'll use metaphones and Jacquard similarity, token intersections. We have not used term frequency and inverse document frequency because it's just too slow. It's been too slow to calculate for us. We need to find a caching mechanism, but it hasn't come up high enough in the priority queue. Jacquard seems to catch most of what we think is probably happening in that. We use administrative location, the location of the death. We'll use simple equality in those, but also adjacency, or the notion of the death having occurred in custody. It's one of the things that everybody is coding for now. Our field teams are coding for is whether or not the death occurred in custody of the Syrian government, and that turns out to be a very useful matching field. We use qualitative locations. We have a little string that says it happened in such and such a neighborhood, or by a big tree, or across the river, or near a bridge, or by where the police station was before it was blown up. And those strings are useful to check for equality, but you can also do edit distance on it and Jacquard similarity on qualitative locations. For dates, we'll do simple equality, subcomponent equality, and integer distance between days. Age similarly has a series of those kinds of measures. So we end up with about 50 features that we throw at a model. And so we'll train a model, and our goal is to train lots of different kinds of classifiers. We'll use random forests, we'll use logistic regression, Bayesian additive regression trees, different kinds of gradient boosting trees, lots of different kinds of classifiers. And we'll defer the decision about which classifier we'll use until much later. What we're really concerned about is less just a raw area under the curve or F1, and more what kinds of pairs do the classifiers tend to agree about, and what kinds of pairs do the classifiers tend to disagree about. We spend an enormous amount of time thinking about the pairs where a logistic regression disagrees with a random forest. Why is that happening? Is there something special about those pairs? Is there, do we find when we compare the classifier disagreement to the oracle's decisions, does one or another of the classifiers do better? That's the kind of thing that an F1 would point out. But are there subtleties that we can find in those disagreements that will allow us to create new, that would urge us to create new kinds of features? And we found a few insights there, but honestly, XGBoost just keeps running away with it. Stacked, we tried a stacked classifier, and so we combined all the different classifiers as inputs into a final classifier, and we really were unable to improve on the gradient boosted trees. They seem to be the winners. They're also more performant than the others we've discovered. We tend to use F1s, but my colleague Christian Lum has a really terrific paper showing that F1 is a pretty misleading measure in the context of unbalanced classes, which these are. Almost all pairs are not matches. Very, very few pairs are really the same person. And in that space, F1s tend to be a little bit misleading. You can have a poor F1 when your performance is actually very good. So, but we use it anyway because even knowing that, it is stable with respect to consistent iterations on the same data. We tend to have pretty good classification, but classification scores, RF1s, tend to be pretty strong. But something we've spent an enormous amount of time worrying about is what is it that we're measuring? What we're measuring is the quality of the classification with respect to one set of training data. How'd you get that training data? Did you pick the easy pairs or the hard pairs? What is a hard pair? How would you know what a hard pair is? Is a pair that's hard for a person the same as a pair that's hard for a classifier? So it turns out to be very difficult. And if you just take the sort of standard approach of using your classifier, your training data, randomly dividing the training data into multiple folds, doing some sort of k-fold validation, you're really doing a very, very best case kind of classifier assessment, because you're testing the classifier on data that's statistically identical to the data you trained it with. Well, of course the classifier is going to do well on that data. It better. If it doesn't do really well on that data, then you don't have a classifier that's any good at all. So what would be a harder test? How do we think through a harder test? So we've come up with a bunch of different ways to think about that, which at the end of the talk I'll tell you why we have abandoned, and we still don't really understand what it means to assess a classifier in this context, and we're really struggling with it. So then we classify the data and then cluster the data, and this is the point when you actually have data that's usable for our subsequent statistical steps to do capture-recapture estimates. The clustering transforms the pairwise distance measures across all the candidate pairs that we've created in the blocking step into clusters of records that refer to the same depth. But there's some issues there, right? So if record A has a strong probability of matching record B, and record B has a strong probability of matching record C, what happens if record C has a weak probability of matching record A? Okay, the problem of transitive closure is very difficult. And the way that we've worked with that is we use transitive closure all the time to define superclusters, and the superclusters partition the data into smaller pieces, and then within each supercluster we will run hierarchical agglomerative clustering to break the supercluster into small, coherent, more coherent clusters. So when we were doing that, we spent a lot of time looking at dendrograms, looking at records that are how hierarchical agglomerative clustering is partitioning a transitive closure set into smaller pieces. Spent a lot of time thinking about that. And we spent a lot of time thinking about entities distribution and entity composition measures. And what we ended up with are questions that look like this. Okay, let's look at these pairs of records. Mohammed Ahmed Greens, which is a somewhat unfortunate Google translation of this man's name. And it turns out we have two records that refer to maybe the same person. The name data and the age category the age data and the age category is missing in the second record, and the death dates are both in different locations and a couple of months apart. Same person? Not the same person. Probably not. Okay, let's look at the second set. Ahmed Qadir Greens and Mohammed Ahmed Greens. Now these guys are only 3 years apart, and we have dates on both of them. We have ages on both of them, and they were killed in the same date and in the same governorate. Same guy? Maybe we feel a little stronger, but hard to say. It's hard to say because Mohammed and Ahmed are often referred to by Syrian people as the same name. Well, okay. How about the next one? Again, different locations, date 1 day off, missing age data. Super hard to say. And what happens, we've discovered, is that our oracles, we have 4 Arabic-speaking oracles and 2 English-speaking oracles who work on this stuff, tend to be aggressive. They tend to agree with each other and say all 3 of these are matches because they're trying to help us be conservative. They know that part of our goal is to not overstate the number of deaths in Syria. That's really important for us. We don't want to be sort of fear-mongering about this conflict. The conflict's bad enough on its own. So they tend to be conservative. They would tend to say all 3 of these are matches. And what we discovered in our flailing around on the hierarchical agglomerative clustering problem is that if we show people the entire transitive closure, if we let the model blow up and say, okay, show us everyone who's connected to anyone in a big cluster, and we show them the entire cluster, people are able to sort the records into subclusters actually fairly more compellingly and more coherently. And what's even more interesting to me, more stably. Inter-rater reliability doing this is much higher than inter-rater reliability doing pairwise comparisons. And this really shook my world, right? Because we do all our assessment based on pairs. We understand everything I can find in this field about creating training data is about generating pairs for a human oracle to review. And what I'm convinced myself of is that showing people pairs consistently overmatches the data and misses these subtle differences among the blocks because that people will pick up on when they can see it all together. They'll use the sparse age information, they'll use the sparse age information and intuitively connect dates that go more closely together and so forth. And we'll end up with a match that looks like this rather than a match that looked like the previous slide I showed, where those would all have been positive. So here's just a little bit of detail on the F measures, which probably isn't the right measure for assessing this, but I have a hammer, every problem is a nail. So we find that cluster-based matching generates much higher F1 measures comparing different oracles to each other than any of the other combinations. So that's super useful for us to know. We also find that less experienced oracles who are on our team tend to be the Arabic-speaking ones, tend to match more aggressively. That people, as they do this for years and years and years and years, and our most experienced oracle has been doing this since 1999, they tend to become more and more reluctant to put records together. And I think that's interesting. I don't really have a substantive explanation for why that is true, except to say that we do see that as a consistent pattern. People come into learning to be oracles and they want to say things are matches. They tend to put records together. And as time goes on, they become more and more skeptical about what constitutes a match. And that seems to be language independent. And then we export the data. So after we've done the cluster, we'll merge all the records together and take modal combinations of fields or ways to exclude missingness and so forth. And I can talk about that in tedious detail, but that's an implementation detail. The point, though, is that the reason we're doing this is to figure out how many people have been killed in mass violence. And the deduplication step is only the first piece. That's the piece that tells us how many people we can identify who've died. And this is a report that came out in August that we did with Amnesty International on the number of people killed in custody in Syrian prisons during the conflict starting in March 2011 through the end of 2015. And we estimate slightly fewer than 18,000, and there's the credible interval. We use a method called a decomposable graphs approach. It's a form of capture-recapture which allows us to make Bayesian estimates. And I'd be delighted to talk about that, but it's fully off point here. So I will end my talk by saying that it's really important that we get this stuff right. We have to be able to have convincing answers for the scale and pattern of violence, not only so that we can explain to the world what the scale of violence is, not only so that we can estimate magnitude, but so that we can estimate a stratified version of that magnitude and understand patterns. Those patterns give us tremendous insight into the structure and planning of war crimes. And this kind of analysis has been used by me and my colleagues in 6 trials for war crimes, crimes against humanity, and genocide, both in international and in domestic tribunals. And we have found it to be a compelling component of the argument that certain people are responsible for this mass violence. So, thank you very much.
Thanks very much, Patrick. So, time for questions. Yes, Christine.
Yeah, I'm Christine O'Keefe from CSIRO in Australia. So thanks for the talk, and I agree it's really important work. I missed, I guess, right at the beginning when you talked about your data sources, but I did wonder throughout the examples whether you've got access to any other data that could help with the deduplication, like many countries run the census, you've got electoral rolls, this sort of thing.
Nope.
There's, yeah, okay.
Nope.
Do you want to say more about that, or just no?
So we've gotten one list. When we started this work in 2012, we were working on contract to the Office of the High Commissioner for Human Rights for the United Nations, and they were able to get one list from the Syrian government. And it really was completely different from all the other lists. It had almost no overlap, no linkage to any of the other lists. And when we showed some of the names on that list to some of the people who were working in the same areas, some of our other colleagues, they said, well, actually, we know some of those people, and they died in 2009. So I would be pretty skeptical right now of any data generated by the Syrian government. any official data right now, I would be pretty concerned about. So there's a real lack of official data. That's not true in all of the places I've worked. Certainly in Bosnia, there was fantastic official data. And I helped out a little bit with a couple of projects that did estimates in Bosnia. And for the Bosnian conflict, we have really, really, really precise estimates now. We have an almost complete enumeration. It's probably within less than 5% of the total conflict. And the estimates that we have using only a fraction of that data line up spot on with the estimate. Spot on with the, just slightly above the enumeration. So in places where we do have good civil registries, Bosnia, Kosovo, Colombia to some extent, we can make the estimates a bit more precise, but it's really rare, really rare. The estimates I've done for Colombia are all based on government registries, but the curious thing is that the Colombian government until 2012 had 4 independent registries of homicides. And I thought this was a gold mine because they were independent, and that meant we could do good capture-recapture with them. And the police have a registry of complaints of homicides delivered to the police. The Attorney General's office has a list of cases that they're working on of homicides. The Office of Forensic and Scientific Medicine has a list of cadavers that they have been charged with making a cause of death determination. And then the military intelligence people kept a registry of deaths in conflict, which was a substantial number of deaths in Colombia during the period I was studying from 2003 to 2011. And there was a 5th data set maintained by an NGO that recorded deaths documented by NGOs and by the press. And these data sets, astonishingly, were barely intersecting each other. I mean, they were very, 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 very different data sets that had little in common, which to me, because I think these were all pretty professionally maintained but with very limited resources and access, suggests that the total number is far greater, in fact double, the sum of the unique count across all these 5 data sets. So I can point you to a couple of those papers if you want, but that's a situation where even when the state is trying really hard and has really competent civil servants working on it, in the context of conflict, their access and logistics and budget capacity is just going to be so limited that they're not going to be able to cover very much of it.
We've got lots of questions lining up, but it's limited. Yes, at the back.
I'm Hedong from Texas, and when I first heard your title, I'm very interested in the topic. I just didn't think it would be related to anything I talk about or my interest, and I realized in your talk we've been working on very similar things because I've been spending time on this oracle, like what's the oracle doing, what's the oracle doing. So
right.
I'm in total agreement with you. You need to give them not pairs, but whatever is the similar blocks. And so in my work, that's what I've been doing.
Yeah.
And then the question relates to, you had talked about how experienced people learn by some way, we don't quite know why, but they change the way they make this decision.
Yeah, slowly.
And I've sort of seen the same, but so my question was, when they are doing this decisions, there's never anything in your process where someday they learn, oh wait, I made an incorrect decision before. So it's like they make decisions, but they never, in your process, there's no feedback so that they can actually correct their decision. It's just, even without that feedback, something's happening such that they're changing their mind.
We have a couple of feedback mechanisms. So we're doing ongoing inter-rater reliability testing. So a lot of the pairs, and I don't know exactly in Syria what our fraction is right now, but in Colombia it was almost all of the pairs were reviewed at least twice. So all the training data pairs are reviewed by 2 different people, and then we have another layer of review whenever they disagree. So, and then we talk about it. You know, I'll say, hey, we've got a disagreement here. Why did you make this decision? Why did you make that decision? So there's plenty of feedback at that level, but it's not. I'm not sure if you want something more formal than that, but that's.
But the thing is, the feedback is still human opinion. So it's like if I'm just thinking about it.
That's right. There's no automated feedback.
But there's no like we've actually confirmed this is the same person or not. So people are learning a group behavior decision making.
I don't really have any way to confirm anything. So. Yeah, what I am doing is piling up subjectivity until there's enough intersubjective agreement that I can convince myself and hopefully the audience that we've made reasonable decisions.
And that does seem like what's happening is actually the group of people who are oracles are actually learning a group decision process.
Kind of, although it's heavily mediated by our inter-rater reliability process. They don't really talk to each other very much. Our Arabic-speaking oracles don't really speak English, and our English-speaking oracles don't speak Arabic at all. So it's all mediated through our pushing stuff back and forth to people.
I'll probably have to stop that. This is a very quick
Yeah, it's really quick.
Okay.
Yeah, quick question. Is any of the data publicly available for other people to use?
Crumbs of it, and you have to write your own scraper. But if you wanted to scrape VDC and SNHR, they're both available online, but you have to scrape it.
Okay, so the data can be made public, technically?
We can't make it public. Our data sharing agreement with the partners is that it's theirs and they're the only ones who are allowed to publish it. So what we can do is publish statistical and scientific pieces about it. But otherwise, if we publish it, then people would come to us instead of going to them and they'd lose all their funding. That's their fear. Whether that's valid or not, we can debate, but it's not mine to decide either way.
Okay, so